Okay, so this box contains common errors that I have seen students over my 19 years of teaching make when it comes to logs. None of them are true. So what I'm about to show you are things that you want to avoid unless you are trying to be wrong on purpose for comedic effect. I get that, right? Okay, so if you have, we'll do the top left one here, log base b of x plus y. If you have multiple terms in your arguments, there is a tendency to want to distribute the log inside the argument. You cannot do that, okay? You can't just take the log of the first and add it to the log of the second. That does not work. And the reason it doesn't work is because the right side, which is log b plus log y, is equal to something, right? When you condense it, it becomes log base b not of x plus y, but of x times y. That's what the right side is actually equal to. Logs take products and turn it into sums. So you can't distribute. So if you ever have the log of an argument with multiple terms, you're done. That's as good as it gets right there. You just stop right there. Okay? Let's work across, left to right. If you have the quotient of two logs, log base b of x divided by log base b of y, there is a tendency to want to pull the log out and just divide the arguments, making it log base b of x divided by y. That does not work. Okay? If you have log base b of x divided by log base b of y, you're stuck. You're done. Unless they happen to be exactly the same, and then they can divide out to give you 1. That's it. You can't do anything with that. This over here, of course, you could expand it. It becomes log base b of x minus log base b of y. But you can't just turn a quotient of logs into the log of a quotient. The bottom right one is tempting. You see log base b of x quantity raised to the power of a. There is a tendency to want to use property 3 from yesterday and bring the a in front and call it a times log base b of x. That doesn't work in this case because if you think about it, what are we actually exponentiating to the 8th power? Not just the x, right? In this case, it's the entire log. So that's an exponent on the log. That means we're multiplying the log by itself a times. So you can't bring it in front. When can you bring the a in front? When it's log base b of x to the 8th power. If it's the argument that has the exponent and only the argument, that's when you can bring the a out front. So if it's the entire log, you got to be careful. You just have log times log times log a times. And then the fourth one here, I gave you an extra example showing you this yesterday. This is another pretty common one. If you have log base b of a times x to the nth power, because that n is on part of the argument, there's a tendency to want to bring it out front. But you can't do that because that n is only an exponent on the x, right? It's not an exponent on the quantity ax. So what we did yesterday is I gave you an example where if you had parentheses around the ax, now the n is an exponent on the whole factor group. Now you can bring it to the front. But without those parentheses there, it's just an exponent on the x. So if you wanted to expand that out, you could, but you'd have to use the multiplier rule first, which says it's log base b of a plus log base b of x to the n. And now in that second term only, now you can bring that n out front. So that's what that's equal to. And if you want to see what the right side is equal to, let's go ahead and do that. If you bring the n up, and this is another thing to be careful of, if you bring the n up on a quantity that's not just a single factor, you are in charge of putting parentheses around it so that it belongs to the whole group. So both of those are equal to something, but they're not equal to each other. All right? So sometimes it's good to see the things that don't work instead of just seeing things that do work, because then you kind of know what to avoid. All right, example 8. Kind of a nice little cute question. This could also be a potential quiz question, one expanding, one condensing, and something like this. This is really neat. So without a calculator, we don't know what the natural log of 2 is. We know it's greater than 1, or I'm sorry, greater than 0, because it's to the right of 1. And because the natural log of e is 1, we know it's between 0 and 1. So let me show you what I just mean by that. You should start thinking in terms of logs. if this is y equals the natural log of x, if you take the natural log of any number between 0 and 1, what type of number do you get? You get a negative number, right? Because the graph of natural log between 0 and 1 is negative. If you want to add another point here, this is the point e comma 1. So now, if you take a natural log of any number between 1 and e, that is between 1 and 2.7, you know you're going to get an answer between 0 and 1. And that's the case here. The natural log of 2 is about 0.7. It's really 0.693. Has anyone ever heard of the rule of 70 from your science class? The rule of 70? The rule of 70 is based upon the fact that the natural log of 2 is 0.7, which when you multiply it by 100, you get 70. It basically tells you how long approximately it takes for a population to double. And so it's built on the natural log of 2. So right now, all we need to know is the natural log of 2 is about 0.7. With that and that alone, I claim we can evaluate or get approximations for these expressions right here. So the natural log of 8, I want to figure out what it is approximately without a calculator using this little piece right here. Well, what that means then is if I only know something about the natural log of 2, I'm going to have to write 8 somehow in terms of 2. Can we do that? Sure. The natural log of 8 is the same as the natural log of 2 to what power? To the third power. Good, right? And now using property 3, I can bring the 3 out front and call that 3 times the natural log of 2. Now I can replace the natural log of 2 with 0.7. So here's where you got to be careful. When you replace natural log of 2 with 0.7, you need a squiggles right there because now it's no longer exact. That's approximately 3 times 0.7. And now I can multiply, and that gives you what? 2.1. 2.1. So the natural log of 8 is about 2.1. That might be good enough for us. Let's see what it actually is. I have a calculator right here. The natural log of 8 is actually 2.079. 2.079. So 2.079 is about 2.1. So we're close. Good enough. All right, part B, the natural log of a fourth. I want to do the same thing. I want to get an approximation for it. What type of number do I know this is going to be? 1/4 would be right around here, right? And so the natural log of 1/4 is going to be what type of number? It should be a negative number, right? But I want you to give me something that's a little bit more exact. Still approximate, but exact. So go ahead and do B on your own. Do the same thing we did on part A. You're trying to write 1/4 as a power of 2, and then you're going to use the properties of logs. All right, so if you want to do it in baby steps, you're trying to write it in terms of 2 because that's the only information we have. So you could say 4 is 2 squared. So the natural log of 1/4 is 1/2 squared. And then you could bring that factor of 2 squared to the top. And, of course, we know when you do that, you change the sign of the exponent. So now we have it as natural log of 2 to the negative second. Using property 3, then, the negative 2 exponent can come out front, and it becomes negative 2 times the natural log of 2. So that's still an equivalent expression. And now since I'm going to replace natural log of 2 with something that's only approximately it, that's where you got to use the squiggles. Okay? And it's fun to not only say squiggles, it's fun to use squiggles. So then you plug it in, you get negative 2 times 0.7, which is negative 1.4. Now notice it's kind of interesting. You've got a 1 and a 4 showing up in the argument, and you got a 1 and the 4 showing up in the answer. Do you think then that in general, the natural log of A over B is going to end up always being negative A point B? You think that's going to work? That would be a good insight, but I think if you tried it out with just like one more number, I think you'll see that it actually doesn't work. So that's just a coincidence. Now, what is the natural log of 1/4? Actually, it's negative 1.386. We got negative 1.4, so again, we're pretty close. Pretty close. All right, we're having so much fun. Go ahead and do it again, one last time. All right, did you get 0.3465735.903? I hope not. That's what it actually is equal to. We want to get the approximation, so pretty easy to write the square root of 2 as a power of 2, which is 2 to the 1/2. Then the 1/2, of course, can slide out front. So you got 1/2 natural log of 2. Then you replace natural log of 2 with something that's only approximately 2, so you put the squiggles. And now it's half of 70 cents, which, of course, is 35 cents, so 0.35. And 0.35 is pretty darn close to 0.3465735.903. All right, I guess I didn't realize there was yet another one. So this one starts off as log base 4 of square root of 8. And I want you to tell me what this is approximately using the fact that the natural log of 2 is 0.7. This one's a little bit more fun. So it requires a little bit more ingenuity. I'll give you a chance to play with it yourself before I just give away the fun. On this one, you may not even need the natural log of 2 to help you. All right, so if our goal is to try and write it not just in terms of 2, but in terms of natural log of 2, this is log base 4. We know using the change of base formula, we can write it in terms of any base we want. So that should be your first step. Write as the natural log of the square root of 8 over the natural log of 4. That's the change of base formula. So now at least they're in terms of natural log. Now you can work on both the numerator and the denominator separately, trying to write their arguments as powers of 2, which will be easily accomplished. That's the square root of 8, so that's 8 to the 1/2. And of course, 8 in terms of 2 is 2 cubed. So there's your new numerator. The bottom, the natural log of 4, that's the same as the natural log of 2 squared. So if you clean it up a little bit now, the numerator becomes the natural log of 2 to the 3 halves, all over the natural log of 2 squared. And now on both of them, we could bring the coefficients to the front. So you get 3 halves times the natural log of 2, all over 2 times the natural log of 2. And if you want, at this point, you could replace the natural log of 2's with 0.7. But you really don't need to, right? Because notice you have a factor of the natural log of 2 both in the numerator and the denominator, and that means that you can divide them out. And they leave a 1. So now we have 3 halves divided by 2, which is the same as half of 3 halves. What's half of 3 halves? 3/4. And that is no longer just an approximation. That is the exact answer. That is the exact answer. 4 to the 3/4 power is the square root of 8. Okay. Let's look at an example. Because you get these in the worksheet, and we don't do enough of them in the notes. But this is really where logs are powerful. They can be applied to things in the real world. So if you've had psychology with Mr. Kilford, you probably have heard about Mr. Ebbinghaus. He formulated what he calls the law of forgetting, or the law of forgetfulness. And here's basically what it says. If you learn something and you don't practice it, then over time you don't remember it as well as when you first learned it, right? Which makes sense. Makes sense. If you've truly mastered something, like riding a bicycle, apparently that is something that you never forget how to do once you've mastered it. But if you master logs and you don't do logs anymore for like the next 30 or 40 years, you might be a little rusty when it comes around to doing logs again, right? That's what his law says. If you learned, this says lean, that should be an R, you might want to fix that. If you learned something and you were tested over it, and you scored a score, call it P sub O. That's the performance at time 0. That would be like your test grade. You make 100 on next Tuesday's test, right? Then, after a time of T years, minutes, seconds, whatever, your performance level P satisfies this log equation. It's a log base 10. So the log of your current performance is equal to the log of your original performance times some constant times the log of the time that has passed between then plus 1. He came up with that, okay? So C is just some constant that depends on the type of task that you're learning. So it differs for tasks. Some tasks are easier to learn than others, right? Like tying your shoe versus learning how to be a concert pianist, right? One of those is easier than the other. There is no quick rule about the rabbit goes around the tree and in the hole that helps you become a concert pianist, like there is for tying shoes. Okay? C is that constant then that is dependent upon the task, and P is your performance level at time T. P sub O is your original performance level. So, part A, solve for P. All right, so we call this a formula, or sometimes we call it a literal equation. Literal literally means by the letter. So a literal equation is just an equation that has a lot of letters in it. In your science class, you call them formulas. We should be able to manipulate literal equations around to solve for any unknown that we want. So in this case, we need to solve for P. So let me go ahead and write it again down here, which is essentially bringing it to my workbench so that I can work on it, my mathematical workbench. All right, so now I need to solve for P. What should we do first? You have a log on the left and you have two terms with log on the right. I would recommend you condensing the right side first. You could immediately go to exponentiating both sides base 10, but that's going to leave the right side kind of ugly, although that would work. So let's go ahead and condense the right side. We want to make this as easy as possible. So what would I have to do first on the right side if I were condensing? Good. I'd have to move the c up. Excellent. So now I'd have log base 10, essentially, of p sub o minus log base 10 of t plus 1 to the cth power. Rewriting the left side, who's patiently waiting, now I can condense. I'll pull 1 log base 10 out front, and because I have a negative term, I know that I'm going to have a denominator. The argument p sub o goes in the numerator, and the argument t plus 1 to the cth power goes in the denominator. Now you have log equals log. So you can do one of two things. Because logs are one-to-one functions, you could drop the logs and equate the arguments, but it's the same thing as essentially exponentiating both sides base 10. So what is 10 to the log base 10 of p? It's just p. And 10 to the log base 10 of blob on that right side is just the blob, p sub o over t plus 1 to the cth power. So this is another equivalent version of Ebbinghaus's laws. But it doesn't have the logs in it. But it's still in the DNA of the problem because this problem is exponential now. The c is the exponent, and so we still have the log in there. Okay, so now part B. If your score on a math test is 90, then you got to ask yourself, how hard did I really study? Probably 10% less than what I should have, right? What score would you expect to get then on a similar test after 2 months or a year? Assume that C equals 0.2. I looked it up, and for learning math, C is around 0.2. Okay, so what do? What are we trying to find here? If we're trying to find which variable? Are we trying to find P sub O, or T, or C? Let's read the question again. How would you expect to score after a certain time period? So we're trying to find P. So this is why we went through the trouble of solving for P first, because now it's solved for the variable that we're interested in. And now I can just kind of drop them in on the right-hand side and evaluate it instead of having to solve each and every time. So let's go ahead and make it specific for our problem. P is equal to P sub O, which is 90, all over T plus 1 to the cth power, which we're assuming is 0.2. So now we've made this problem very, very specific for this particular scenario. All right, so let's just call the first one part A. What are we measuring T in, by the way? It doesn't really say. So let's go ahead, and I probably should have written this in here. T is measured in months for this problem. That's something I should have written into the instructions. All right, so on part A, we're trying to figure out the score after 2 months. So that would be P of 2, essentially. You plug that in, you get a 90 over 2 plus 1 to the 0.2 power. So this is where now you can go to your calculator and type it in. And I'll go ahead and do that. If you happen to have a calculator, you can use it. If you don't have one, no big deal. This is not a very difficult calculation. 90 divided by 3 to the 0.2 power. Should it be higher than 90 or less than 90? Yeah, that'd be great if it was bigger, right? That'd be some kind of law. Learn something at a certain level, forget about it for a while, and then you get better at it. Right. I played chopstick 20 years ago, went back to the piano, and I started playing Mozart. Wow. If only it were that easy. You end up with 72.246. So if you scored a 90 on the math test, and then 2 months later I just gave you a pop math test that was the same test as 2 months prior, according to his law, you'd still pass with a 72, right? Which might be kind of like an 80 after the curve. You're welcome. You're welcome. All right. Now, if you walked away for a full year, your skills should atrophy even more. So now, after a year, P of what? If we're measuring T in months, Yeah, P of 12. Good, P of 12. You get 90 all over 12 plus 1, 13 to the 0.2. You think you're still passing this test? Probably not unless you get to do a little bit of rehearsal or review. You end up with a 53.88. Yeah, not so good, not so good. So it decays over time. All right, so there's a nice little application. A lot of social models, a lot of scientific models are based upon log functions. So here's just one more example. Y'all had in the last worksheet the Beer-Lambert law. You remember reading about that one? The Beer-Lambert law is a log function that deals with light absorption in the water. Apparently at the bottom of the Mariana Trench, it's dark. I've never been, but they say it's dark. Even on a bright sunny day at the surface, it's dark at the bottom. You lose light as you go down, according to a log function. All right, then example 10. I really like example 10 because it gives us a novel way to use the change of base formula. Because we can use the change of base formula to write equivalent equations of the same logarithmic graph. So if you recall in the previous sections, we found two different equivalent ways to transform a function into the given function, okay? Kind of turning an a value into a b value or vice versa. We could do the same thing with log functions using the change of base. So here's the task that we want to do. Describe how the graph of f of x equals log base 1/2 of x. That's logarithmic what? Growth or decay? Decay. Good. The base is a half. How can we take that graph and transform it to become the graph of log base 6 of x? All right. Verify your graphing calculator. Let's see. I'm going to give myself a graphical task. This is the point 1, 0. Log base 1/2 is going to look like this. That's f of x. G of x, I'll draw that one in green. It is going to be logarithmic growth, base 6. Now, which graph do you think is going to be steeper? We essentially have a log base 2 that's flipped versus a log base 6. If you remember for log functions, the wider the base, the steeper the graph. Bigger or smaller? The smaller, right. The smaller the base, the steeper the graph. It's the opposite, essentially, of exponentials. So if log base 1/2 can be basically a log base 2 that's flipped across the x-axis, then log base 2 should be steeper than log base 6, right? So when I draw my log base 6, I'm going to draw it a little less steep. So kind of, whoops, goes like that and tapers off. So if you were to flip the red graph across the x-axis, it would be above the green graph to the right of the x-intercept and below it to the left. All right, so that's my g of x function. So what I'm trying to do now, I want to describe the transformations that it's going to take to turn my red graph into the green graph. And what's the most obvious thing that we're going to have to do to the red graph to turn it into the green one? Flip it across the x-axis, right? So here's what you could say. You could take your log base 1/2 of x. If I flip it across the x-axis, that's going to make the a value in front negative, right? And then because the g of x is less steep, I'm going to have to vertically stretch it or compress it a certain amount. So in other words, all of the transformations that are going to be involved can be assumed through just the letter a in the front. A is going to be a negative number, then it's going to be some amount that allows us to stretch or compress it so that they line up. So if I take log base 1/2 of x and multiply it by some a accordingly, I can turn it into a log base 6 of x. So essentially now what we have is we have an equation, and we want to solve for a. Doing something to the original graph by multiplying by some a can turn it into the log base 6 of x. And because we've already seen it graphically, all we really know about A is that it's a negative number. All right, so how are we going to do that, and how is the change of base going to help us do that? Well, are the bases currently the same? They are not. So let's go ahead and turn all of these fruity products into apples. Right now we have oranges and bananas. You heard about comparing apples to apples, right? Let's go ahead and turn the bananas and the oranges all into apples by putting them into base what? What's our most comfortable base that we work with in here? Not D, the letter right after it. E, right. Yeah, okay. That's what you said. So let's put them all in terms of base E. So we're going to get the natural log of x over the natural log of a half. And over here we get the natural log of x over the natural log of 6. And all we got to do is solve for A, right? Well, that's not difficult anymore. All I got to do is multiply both sides by the reciprocal of the natural log of x over the natural log of a half. So we get A equals, the right side stays the same, and then times the reciprocal of the one on the left, that's the natural log of half over the natural log of x. What happens to the natural log of x's? They divide out, yeah. And we're left with A equals the natural log of a half over the natural log of 6. And we're essentially done. That's a number. That is definitely a number. But I probably wouldn't leave it like that because it looks kind of like a complex fraction because you have the natural log of 1/2. So here's what I would do. I would change it up just a little bit for like a multiple choice question. I would call the natural log of 1/2 the natural log of 2 to the what power? 1/2 is 2 to the what power? Negative first, yeah. All over the natural log of 6. And now I could bring that negative out front and say it's negative natural log of 2 over the natural log of 6. And now we know for sure, since the natural log of 2 is a positive number and the natural log of 6 is a positive number, now we know that A is for sure a negative number because we got a negative right there in front. So that's the answer. That's the answer. Now it says to verify graphically. So in the time that remains, we'll do that. Got to wait for my calculator to load. All right, so let's review while the calculator's loading what we did. We put the A value, which of course is responsible for the x-axis reflection and the vertical dilation, we put it in front of the equation that we start with. You always put it in front of the equation you're starting with, and then you want to see what A has to be to turn that graph into the graph on the right. All right, so now to verify on the calculator, if I graph in y1, let me go ahead and write this out. In y1, if I graph negative natural log of 2 over the natural log of 6 times log base 1/2 of x in y1, and in y2, I sketch log base 6 of x, what should happen when I graph both of them on the same coordinate grid? You should see how many graphs. The answer is 1. All right, so let's go ahead and do that. Natural log of 1, we're going to go ahead and plug in the A value that we found, so it's a negative. I'll use the horizontal division bar, that's alpha y equals the natural log of 2, close parentheses, divided by the natural log of 6. So there is the A value that we found. Now, to type in log base 1/2 of x, remember, you can hit alpha window and then select number 5. That's what's nice about MathPrint. You could type in the base as 0.5, which is the same as a half, and type in your x. In the blue one now, we'll just type in log base 6 of x. So that's alpha window, choose number 5 again, log base 6 of x. Now before we just hit graph, let's think about a reasonable window. Both of these are going to live to the right of 0. So if I set my x-min to -1 so I can see the y-axis, 10 looks like it should be good. And negative 10 to 10, yeah, that looks all right. I'll see how that looks. All right, so when we hit graph, we'll see the blue graph coming in first, and tracing on top of the blue graph should be the red graph, right? Here we go. Blue, red. Because you only see one graph now, that probably indicates that you have the right value. Of course, you might want to go to your table of values. If you hit second graph, you go to the tables, and now you can compare at different values of x, the y values of each function. And if you notice, to the 4 decimals that are showing, they're exactly the same. If you want to get more decimals, actually scroll over into the column and notice, because the calculator is graphing them in 2 different ways, what do you notice about the last decimal digit that shows at the bottom? It's different, right? By 1 unit. So notice that it's accurate to however many decimal places that is, but the calculator is graphing them by 2 different means, but we do get the same graph, okay? So there you go. Let's give you all a chance to do this one on your own. So try it by yourself. We want to start with, let's say y equals log base 9 of x, and we want to end with, turn it into a y equals a log base 2/3 of x. What is the value of a? Let me help you set it up here. Remember, you want to put the a value in front of the one you're starting with. So it's going to be a log base 9 of x equals the one you want to end up with, log base 2/3 of x. So go ahead and figure out what the value of a is. Put the unknown in front of the starting function. While you're working it, I'll work along here with you because we've got about 2 minutes left. Putting everything in terms of the natural log turns all of the fruit into apples, so you can compare things. Then you multiply both sides by the reciprocal, and you don't even have to show all the steps. You end up with the natural log of 9 over the natural log of 2/3. You can end it like that. Now, what I would do in the denominator, because now we have a fraction in the denominator, I would probably expand that and call it the natural log of 2 minus the natural log of 3. So that's one way I can write it on the answer key on the answer choice. 9 is the same as 3 squared, isn't it? So the natural log of 9 is the same as 2 natural log of 3. So perhaps I would do that as well and make this the answer choice on a test to get you to kind of play around with logs a little bit more. But you have targets. Your answer choices are your targets. But it all started with setting up this equation, putting a capital A in front of the equation you're starting with, change the base formula, solve for A. All right, there's a minute left, so that gives you time to pack things up. The worksheet is due tomorrow for 4.4, and we'll have a couple of quiz questions. Expand, condense, and probably one either like this and or one like example 8. Okay, so maybe 4 questions. Have a good rest of your Tuesday. National Blue